Oh no, it looks like it's recording. Okay, cool. So continuing on what I was saying. So yeah, I mean, in functional programming, you are kind of keeping state, except that your state is now on the stack, I guess. And yeah, I mean, like it is kind of like a matter of preference, but in some cases, I guess it does make the state of the application more transparent to you, so you know exactly where things are going wrong.
I think it depends on the application, definitely. I can't see how in like embedded programming, not like change of state is kind of like a requirement, but it's like you have to, like you can't
Yeah,
really
like there you just
forego
like
that. I don't.
yeah, like in the end, you just have to have like a couple like static variables or kind of global variables for
Yeah,
everything, right? And especially if you're dealing with like
yeah,
your management and all that kinds of stuff, you don't really have that kind of luxury to yourself. So yeah, I don't
yeah.
know. I actually need to look more into like that uh, functional
Quick
programming.
aside here,
Yeah, me too.
Know much about it.
I know very little
there's a
about functional
topic.
programming.
Yeah.
If you guys can watch a YouTube video. I remember watching it like a year ago, and it was something that kind of revolutionized the way that I think about programming.
Yeah.
I think it was called something like object-oriented programming was a mistake,
Oh.
something like that. And it's such an interesting, such an interesting talk, and it kind of goes into, you know, we're kind of taught that object-oriented programming is the way to go. It's supposed to be the solution to everything, but there is a big argument. There are many big arguments as to why this is not necessarily the best way to handle things. And you know, I think that the guy talking about it makes a point against it and towards like purely functional programming. I think at the end of the day, you should know both and use the best one for the occasion.
Yeah, I think that I agree with what you're saying. Like knowing both is always best because it kind of helps you. Okay, let's see. What does last Zoom recordings want? All right. Yeah. Oh no, that's good. Okay. We're good. All right. So let's go over the rest of the problems.
Yeah.
Who else? Yeah. So variation 2 of Vlad. Are you gonna go with this one?
Sure. It's gonna be real quick because I didn't have a question for it right away. But yeah, let's get into it. Also, okay. I think I should share my screen. Like, I think the person that's talking should share their screen. Yeah. Because otherwise, it's very hard to follow where you're talking about, I think.
Okay. Yeah. Sure. Share your screen. I don't think I'm sharing my screen right now. Am I?
Host disabled attendee screen sharing.
Wait, really?
Why you do this?
Multiple participants can share simultaneously. Okay, you can go ahead now.
Holy moly, what is going on? Why do I have so many?
Zoom recently updated, which is why it's like a little bit weird.
What is going on? Let's try this. Oh man, I have to open system preferences now to give it permission.
Oh, you might have to exit Zoom and come back in again.
Oh Lord. Yes, bye-bye.
All right.
This is pretty nice.
Be on the recording. Oh yeah, how are you enjoying this, Sina?
It's pretty nice. You guys are pretty hardcore at it. I like it. For me, it's like I forgot what heaps are pretty much, and you know.
And then you just go, yeah, I like it. I mean, personally, I wouldn't, go this deep, but I feel like it's just like the pressure of the group because people are fucking keeners. And then, and then I just like see Vlad going off or like Ziad going off and just like looking at all these stuff. And I'm like, all right, I can't not do anything.
No, dude, by the way, Sina, like,
what are you talking about?
Heaps, guys, we didn't know, Heaps, not didn't know, but like, personally, I didn't remember anything about Heaps until last week, which was the problem set that we kind of went over with in great depth and detail. And so that's why this week's Heaps are a lot easier to
you master it and everything.
Yeah. So Vlad, Sina was like, while you were gone, Sina was like, I like this and how we are like really hardcore at like everything.
Yeah, that's good. I won't stop you there. You can continue, Vlad.
All right, let's go over the problem. Wait. Vlad, pull up the problem first.
Oh.
You don't have the problem ready, huh?
I have it somewhere.
I should screen share now.
Where is it? I'll find it. Oh, goodness. Arshin and Vlad. I think that's the name of the thing.
Yeah. I need
Okay.
to add. I need to change it so that it's like Arshan and Vlad and Ziad, and potentially.
11 point. There we go. Okay, so this one is loading. This ain't it.
So so I can read the.
There it
problem.
is. Okay. Design an algorithm for finding the kth largest element of A in the presence of duplicates. So that means when the kth largest element is defined, the kth largest element is defined to be A of k minus 1 after A has been sorted in stable manner. So sorting is from like lowest to greatest. So it wants basically if there's duplicates, it wants the first one of those duplicates. But it just says you want to find like the kth largest element. So it doesn't need to actually be that exact element from my understanding. It just needs to be one of the duplicates, but not exactly the first one in that order. Am I wrong? So because that changes a lot, I think. So like, let me just explain exactly what I just said. So when you sort it in, let's say there's duplicates, right? And you sort it in stable manner. And say there's 2 5s, and say they appear in index 2 and 3. So basically, what's interesting or what I don't know is if we just have to return like 5 as being, because like say 5 is like the 5th largest element and the 4th largest element. I guess. I just figured out the problem. So let me explain to you the problem I had. So let's imagine the 5 is like the 3rd largest element, but then there's the duplicate. So technically the 4th largest element would be the next one. However, it's not actually like the 4th element in sorted order. So the problem arises like if you want to find, let's say, the 2nd largest element and then the 1st largest element, there's like 5 of them, then your 2nd largest element is actually the 6th element in sorted order in terms of like largest. So I didn't solve this problem at all. That was my problem. I didn't understand what the difference was of this problem, but now I just understood the problem.
Interesting.
So it's very fair because the problem statement wasn't really clear, and there was something about it that confused the heck out of me as well. I think I was in the same state as Vlad here.
But yeah, so like for instance, what I'm saying is like, let's imagine this is the list, like that. Can you guys see that?
Yeah.
Then the sorted order would be this.
1, 2, 3, 3. Yeah.
And if you want the first largest, that would equal to 3. And then the second largest would equal to 2. But
okay, that's how we're defining it. Okay.
Let's say this is A and this is A sorted. Whoops.
Okay.
Then what's interesting is that now in A sorted, sorted at index, what's the index? Minus 1 minus K. Whatever. Yeah, that's right. No? You can just do minus K. So like, yeah, that'll work. Where K is the first largest. So let's imagine K equals 1. So then this equals to, or I guess returns 3, which is great. But now if we do the same thing, but K equals 2, which you would think is like the second largest, it still turns 3. And so this is
the nth largest.
So you actually want to return the nth largest element in the presence of duplicates. So like the second largest actually means like 2, not like the second element in sorted order.
So second largest element by value.
Yes. And so now I'm assuming none of us have solved this problem.
I don't think so. What do I even have for that problem? Let me see.
Don't you like find this number of like you kind of have to keep a number of how many instances of like a certain number you have, and then you just
I don't know. What do you have? What is a variation term?
It would be.
Oh, very nice.
Huh. That's a little bit weird, actually.
So
Because
you did.
if you want to base it off of like the quick sort kind of select or quick select approach that we had, with quick select you kind of just land on that element.
Yeah,
right?
you land on that element in the list. That's what I'm saying. Is like you would land here, so this would be your whole thing.
So you're like, if we have something like that, and it's gonna be a little bit weird because we have.
Guys, I have a solution.
Oh.
I have a solution. Watch this. This is what we do. We just go, and we do we take our non-sorted list, and we set it equal to a list of a set of a non-sorted list.
Oh.
So now there's no
you're
duplicates.
Gonna get rid of all of the duplicates, right?
Yeah.
And then just call the same thing on. Yeah, that'll work.
That solves the problem.
that definitely solves the problem. I mean,
And it's linear.
Problem.
Oh wait, is it linear? Oh, creating a set is not linear. It's like n log n or something because you have to sort it and then delete or something like that.
No, you can do it linear time.
There's no, because you have to find duplicates, right?
Yeah, but you can implement the hash table and then see if it's in the hash table, and if it is in there, and you can do it, and then you can enumerate all the keys in the hash table. So yeah, it can definitely be linear.
Close to linear, I think.
No, it's
you're like,
exactly linear.
oh, because when you create the hash table, you can just keep a count of how many elements are for each like duplicate thing or something.
Oh, you don't really need to even keep accounts of them. You can just like put it in the hash table if it doesn't exist.
If it doesn't exist, oh yeah, that's right.
And then like every insertion in the hash table is going to be constant time, and then you can just enumerate all the hash elements.
That's actually beautiful. I didn't think of this. I always was like, whenever you said, I was like, fuck, this is like probably n log n, I think. But I didn't.
Hash tables are everything.
No, I know, but I didn't realize that making it, for some reason, I don't know, I thought making it wasn't oven, but it is oven.
It is, yeah.
Oh, that's beautiful. But yeah, this would be like the solution. I feel like this this is a solution. And then do the problem.
I remember watching a video once, and the guy was talking about hash tables, and he describes hash tables as a cheat code because there's so many problems that you don't actually have to solve if you just use hash tables.
Yeah.
They're like those cheat codes you would put into your like PlayStation, like Street Fighter or whatever. That's what a hash table can do.
No, that's so true. That's
it's honestly that.
Yeah, hash tables are lifesavers. Like whenever your algorithm, like every time you're doing anything dynamic programming, first approach is usually brute force. Second approach, okay, now I want to like keep track of some of the stuff that I did. What comes to mind? Hash table, and it'll like drop a couple ends from your like complexity.
They're super flexible. Yeah, they let you do stuff. They let you keep track of multiple things at once. They let you like I don't know exactly, can't pinpoint what it is. I think they're just like really flexible and you can use them for so many things. There's so many problems where you need to keep track of related things, and you can do that with hash tables.
Yeah, I think that the kind of determining factor for me is like the constant time insertion and constant time lookup. The constant time lookup is just a lifesaver for me.
Well, aren't arrays are not. Wait, no, arrays should be.
Arrays are also a constant time lookup, except that the key is a number, whereas in like hash tables,
they're not constant time lookup.
Arrays?
Wait, no, arrays are
for a value. They're
no,
constant time lookup.
Constant lookup by index. That's what.
Yes. Yeah.
Yeah, lookup by value. No,
but that's not very useful, I guess, unless you know the order of your array.
Exactly.
Yeah.
All right, cool. Let's continue.
Let's just go on to the next one. Can you guys see this other screen?
Yeah.
Oh, cool. Okay.
I'm seeing your PyCharm session.
No, can you see my Google Chrome?
No, I can't.
No.
Oh, I was reading the problem, and I was like, huh. I realized you guys can't.
Bring the problem into this screen.
Oh, I have it on a browser window.
I think you just need to change your share. Oh, yeah, that's it.
That's fine. I'll just switch this.
Look at you using my screenshots.
Yeah, man. All right, this one was funky. Like this one actually took so long to understand what was going on in the solution. So I don't know. I think it's like very interesting though.
Yeah, it
So,
is an interesting solution. No problem.
okay, so you have a number of apartment buildings.
Yeah.
And they're coming up on a new street.
Yeah.
And the Postal Service wants to be logical and place a single mailbox on the street.
Mm-hmm.
And their objective is to minimize the total distance that residents have to walk to collect their mail each day.
Mm-hmm.
So different buildings may have different numbers of residents, and apparently they somehow know this exact number of residents, and they're just going to base this on the current state of residents, and does not depend on the future that people will move in or anything. So yeah, so then given that current state of people and how many houses there are, and you know all that, you want to devise an algorithm that computes where to place the mailbox so as to minimize the total distance that the residents travel to get to their mailbox. And assume that the input is specified as an array of building objects where each building object has a field indicating the number of residents in the building and the field indicating the total distance from start to end. Yeah. So basically, you can imagine that that you're given how far each building is from like some index 0, from like, and then you know how many people are in each building, and you want to place a mailbox at some distance away from distance 0. So you just mark some distance 0.
Yeah.
And then houses are.
I saw in your test cases is that all of the buildings are just like inserted one after another. Can't you have like an empty space?
So like I do, but I put 0 residents there.
Oh, gotcha. Okay.
I believe. Let's just double check. Where the hell is this?
Do we have a test case for that?
Pardon?
Do we have a test case? Yeah. Yeah. In test case number 1, there's 2 people in the building with 0.
Yeah, the distance of the building is 2, and there's 0 people there.
0 people in it. Okay, cool.
And there's 0 here.
Equivalent to like not having anyone in there.
Yes, I just did that for the ease of writing this because I was like kind of lazy and didn't feel like thinking of something better. Can you see this screen? The pie chart?
Yeah, yeah.
Okay, how do I move this graph? Why is it do you see this thing stuck on top?
Yeah.
I don't know how to something better. Anyways.
Do colon B split.
Oh no, I was just talking about the thingy, the zoom window. Okay, anyways, so here's the solution. So you'll notice the indenting is, or the line length is still 120 when I did the solution, so I didn't fix that, and I don't want to fix it now because I feel like it's going to look a little weird if I just auto format it. So we're going to look at it in this nice long view. Okay, so the idea. So let me just explain the idea before even going into the code, because I feel like it's going to be very confusing otherwise. So the idea is actually to use exactly what we just talked about, surprisingly enough. So what you do is you place the mailbox somewhere, anywhere you want, and that's kind of like your pivot. And after you place the mailbox, you then count at how far away it is for all the people to the left of the mailbox, so a distance less than. I guess so we're gonna say, like, once again, just I want to mention it again, is that we mark some point as being index 0, as being like the leftmost part of all the buildings. And then we mark all the buildings to be some distance relative to that index, and the mailbox placement to be a distance relative to that index as well. So yeah, so once we place this mailbox randomly, which is, I guess, our pivot in this case, and we then can compute the number of houses and the amount of distance everyone in that house must walk to the left of that mailbox, and store that as which I use in this total residence and distance data structure. And the distance to mailbox, this is a total sum, and the number of residents is going to store all the number of residents. So this data structure is going to store all the residents to the left of this new mailbox placement, and it's going to store the the sum of how much everyone needs to walk to the left.
Yeah.
You do the same thing for the right, and yeah, and then the people on top of the mailbox, they don't have to walk any distance. So that's not, we don't really need to store that. So then what you do, you're like, okay, great. Like, I know, so now you can sum them together and you know the total distance that people need to walk. And that's great. But then you want to know, like, is this a good place? Is this a bad place? And then the beauty arises that you realize, okay, like, how would I know that? Well, like, let's think of a really like logical case. Like, imagine you place like really far to the right? So like almost everyone's to the left, and then there's like one building to your right. So like, obviously it's better to move it to the left.
Yeah.
Because there's so many people there. So moving the mailbox one step to the left will be beneficial because so many people on the left will benefit. Like literally it'll be closer to every single person on the left by 1. So it's the number of residents on the left. It's gonna the total distance from the left people is gonna be equal to the previous total distance minus the number of residents to the left, because it's gonna be one step closer for everyone. If that makes sense. And then for the right one, it's gonna be more distance for everyone to walk. So it's gonna be the previous total distance for the right, but plus the number of residents that exist on the right. And in the case that I mentioned where there's a lot of people on the left and very little on the right, it's very logical to move it to left, because you like decrease the left count by so much. So that's basically that check of which way you're going, left or right. How we previously had the check to be like, is it the kth largest if it's less than or greater than k? It's now simply moving one left, moving one right. Is one of those better? And you can't have both to be better. That's not possible. So that's not a problem you run into either. So it's basically checking if one of them is better, and then whichever one of those you move. And if it's not better, then you just stay in that place and return that value. So we can get into the solution. So if you look here, this is where we start. So we have a start, like this part. We have a start and end distance, which is literally the entire range, which is the max of the buildings dot distance. And the buildings are the thing we pass in. Yeah, it's what we pass in. So it's all the buildings, and you just find the building that has the largest distance to the right. So then you know like what the mailbox range that you can put it into is the farthest distance to the right and from 0. And then, so then we just keep looping over it. And what we do is this right here is basically like the pivot, which is the mailbox distance. So it's just a random distance from start and end distance. And after that, we want to basically get the totals, which is like the total distance, which is actually going to be that data structure that I mentioned up here, the total res and dist, which gives you the number of residents and the distance, the total distance to that mailbox. So if we go back here, you can see that this data structure here is before the box. So that's for all the people that are left of the mailbox. Then you have just the number of people at the box, because you also want to adjust for them when you shift to left or right. And then you have this one, which is for all the people to the right of the box. So this is like the most important part, because once you have those, you can do exactly the updating, like I said. So this, for now, just this get totals basically gives you all these, given that you give it the mailbox distance. So it just calculates it. I mean, you literally just give it the mailbox distance, and it just calculates for you the total sum to the left, the total sum to the right of people walking, and then it also gives you the number of people from the left and right, and just returns that. So I think that's pretty logical enough, or pretty easy enough. And then after that, you get the current total distance, which is just the left and right together. And then after that, you set a new variable to get, that's basically if you go right one, which is +1, or if you go left one, which is -1.
Yeah.
And then you do the checks. So if you go right one, or if going right one is less than the total distance, which is great, then you set your start distance to just be the current mailbox distance +1, because you know it's somewhere that's +1 to the right or farther. And then you do the exact same search again with that new set of bounds, which is exactly like literally problem 11.8, where you set the new start distance. And then the same thing for the end distance. So if you moving left one is the more beneficial one, then you just set the end distance to be left one, because you know left one's already better. And then the other case is this is the case when the mailbox is actually the best case. So moving left and right is not good. And then you just return the mailbox distance. So this was like super, super interesting. the stepping one to the left or stepping one to the right.
So I did this in a different way. I like your solution. So let's come up with the complexity of this. So let's say, let's just do like average case complexity.
Yeah, so the only,
that's reasonable.
Yeah, so I think the only difference actually, and I think it could be improved, but I was just kind of lazy. So runtime would be big O of, so let's say there's, so the mailbox could technically be placed, this is kind of funky, because the mailbox could technically be placed in any of the distances.
Yeah.
So if like it's really sparse, you're kind of getting slapped.
So like, let's see, you have the buildings, right?
So like, yeah,
you have n buildings.
So
and on average, like m people in each building. And for simplicity, let's say your distance can be n for now. So you have buildings of 0 people.
Yeah, with the buildings of zero, like I mean, so the mailbox can technically be placed at every single possible distance in the worst case, right? And that like range of distances is like the farthest house
Well, no,
minus
it becomes
zero.
like basically like if you have n buildings, then it can be placed anywhere from 0 to n minus 1.
Well, actually, the way I do it is you can. So it's hard to know. Well, actually, I guess if you do that, if you keep your random placements to only on top of buildings, but what if the
Well, no,
placement is better
you can
between buildings?
you can specify a non-building with a building with 0 people in it.
Yes. Oh, okay. So you're
So you
saying
can fill up all
let's
the empty spaces with empty buildings.
yes. Okay. So yes. So it'll be the number of buildings.
Yeah.
But in reality, that's just like a filler way to do it in for testing. But in reality, what you could have like one building at location 0. Let's imagine
And
like
then one building at location 5.
or location 1,000,000. Then you have 0 stuff in the middle, and you imagine placing the mailbox one at like constantly getting the random number to be at one less than 1,000,000, then one less than that, and then one less than that. So that would be
Yeah.
terrible, right?
Yeah.
Yep.
So it's like farthest, yeah. So it's literally farthest building minus 0, and
Mm.
we'll call that A. And so it's that time. So that was the original.
So for now, let's just assume that all the buildings are set next to each other. Or
Yeah,
not.
but yeah, I mean, this is fine because like, and then in the worst case, it would be A squared. That's like the worst case, but it should on average be A. But then the problem is when you get this totals, because getting totals causes you to iterate through all the houses each time.
Yeah.
And that could be way quicker if you just save the previous one. Because like every time you make a shift, it's just literally updating all the houses except for the, oh, actually, I don't know if you can do that. Oh, what you could do is you could just have a running sum
Yeah.
or something like that. But yeah, this is like
But
an
do something
inefficiency.
like that to kind of make this a little bit faster.
Yeah, but
Not a
that's,
little bit, but like a lot.
yeah. And then, yeah, so it'd be like this and possibly like that. I don't know.
No, I don't think it'll be 8 to the power of 2n. Would it be?
Well, 8 to the power of 2 times n,
Yeah. Yeah. That makes sense.
like that.
That's worst case though.
Yeah, that's worst case, I think. Yeah, this total get total.
Best case though, I don't think it'll be O of A though. Would it be?
So best case, it's
It'll be
okay because it's exactly the same as the other way we like what we did before. Because you keep breaking it down into ideally half and half and half, and then you're constantly finding random mailbox placement within that new range, and the get total gets like constantly smaller and smaller, right? Because oh no, you always have to do it over the entire set of
Yeah,
people.
so you are iterating over A. So like in every kind of iteration, you loop over A.
Well, n the number of buildings, but yeah, like if we
Number of
assume
buildings. Yeah, sorry.
that we
So you
assume
loop over the number of buildings to calculate the total weight kind of thing. And then
yeah. So this
again, you
part's
break it down. So to reach the best building, you will need to do this how many times? Worst case scenario, like A times. And every time you calculate A.
yeah. Well,
So
it's
worst case scenario is A squared n.
yeah.
Best case scenario is, well, if you just land on the building. So best case scenario is just n.
Well, I think the average should be still
Average
that.
case should be such that, yeah. So
Yeah, I think it's still. Oh my goodness.
average case still will be A squared, I think.
I don't think because it should be the exact same thing as the other one. Like it's literally the exact same thing, right? You're constantly breaking it up into like sub problems that are dictated by the random pivot placement.
Wouldn't
And the
it
random.
be A log A on average case? Because you split it in half, and then you split it in half, and then you split it in half.
But that's assuming you don't find the mailbox placement, right?
Yeah.
Oh,
So you
but
would
wait,
probably, because you either land on the mailbox.
yeah, but wait, why was the, because like, why was the 11.8 O of A on average,
Oh yeah, you're right.
right? That like, I mean, it follows the
Yeah,
exact same
because
principle.
we still did the same thing. Yeah.
It's O of A because you are. It's not log. Is it log? No. Wait. Yeah, because like that's the worst case. It would be like O of 2A, or like on average it would be like O of 2A, right? Because it would like do like the full. It would go through the full list,
And then over half of it.
and then half, and then one, and then half of that, and half of that, which just approaches 1 again, or the full list.
Yeah, it approaches the list again. Yeah,
Yeah.
that makes sense.
While log A is literally going over the full list log A times, but we don't do that.
Yeah, we don't do that. Okay, yeah, that makes sense.
I think. But binary search, wait, binary search, that's log A.
Yeah.
Yeah, so that makes sense. I think.
Because it's because, well, you are going through it. You might loop through it like log A times, but the size of the search space basically reduces
Yes.
by half every single time. So
Yeah,
if you
you loop
start
through it log A times.
So if you just start adding them, it'll be like n plus n over 2 plus n over 4 plus all
Yeah,
the way to
yeah.
like 1.
Which
And that is your average.
goes to 2n.
Yeah, and that is the case where you pick your pivot such that your pivot basically lands in the middle,
Yep.
where you can get rid of like half of your list and then you pick another pivot.
Yeah.
All right, cool. Also, this meeting will end in 10 minutes. Let's start another meeting and then I'll show you my solution.
Okay, wonderful.
All right, cool. And